see ourselves over here. There we go. Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is Professor Ninghui Li. He's one of the core faculty here at Purdue involved with CERIAS. He's a faculty member in the computer science department. His talk today is on membership privacy, a unifying framework for privacy definitions. Mm-hmm.
Thank you, Randy. The work I'm presenting today will be presented at the ACM Conference on Computer and Communication Security next week. And this is a joint work with my former PhD student, Wei, and my current PhD student, Dong Su and Wei Ning Yang, and also with Professor Yi Wu from our department. So this is the outline of the talk. First, I'll describe some privacy incidents as both the motivation for satisfying privacy when you publish data and also for motivating the exact choice we made in terms of membership privacy. And then I'll talk about the history, a brief history of privacy notions. And finally, I'll talk about our proposed membership privacy framework and what we can do within the framework. So we all know we are in an information economy. So you can say data or information is sort of the fuel of the economy. Data drive all kinds of innovation. But to make the data most valuable, we really need to share the data. There are many situations that data sharing is critical. For example, social science researchers need access to different kinds of data to do their research and to come up with policy recommendations. And medical research relies on all kinds of data, both medical record and also genomic data, and also all kinds of technological breakthrough nowadays are based on sort of having access to data. So lots of companies basically build their business model where having access to data and have the ability to share the data or to use the data effectively. And also data sharing is often mandated by laws and regulations. U.S. government by law has to share census data. So every 10 years they collect census data and then they have to share some version of the data with the public for various purposes. And also there are situations that we want data sharing in order, for example, to improve the security of the overall internet. So we may deploy sensors in different places in the internet and then collect the data from them and then do analysis. But the data we collect may be, because they are deployed within different networks, they may include privacy sensitive information. So sharing them is not as easy as one would think so. And also all kind of business decision will require access to data. And also an interesting sort of usage scenario for sharing data, sort of the need to have access to data is actually for testing of systems. So when you have I heard this from a a security officer from Target who visited CERIAS. So he said that before they deploy their system, they have to test the data, use real-world data set, using data set that have a real-world significance. But then they can't really use real data set because there's privacy concerns. So many situations require sharing of data. However, publishing data can also result in privacy incidents, which can have serious consequences. So I'm going to describe 4 well-known privacy incidents. So the first one is by this company called the Group Insurance Commission, who is basically a health insurance company for the public employees of Massachusetts state. So they have the patient record of all the public employees of Massachusetts state. And then they make this data available for researchers, and they also sell them to industry. So you pay like $50, you can get some version of the data. Of course, they know they can't share the raw data because that will be obviously violating privacy. So what they do is they first remove all the explicit identifier, for example, name, and also anything like a telephone number, address, where you can easily link to identity. Those information are removed, and then they think that is fine. So then they sort of make this data available. But then Latanya Sweeney, in a paper in 2002, showed that remain in the shared data set is sufficient for you to uniquely identify many individuals. In particular, the data include date of birth. So here I use age, but rather it's date of birth, and also the gender, and also zip code. So if you think about it, these three pieces of information is able to actually uniquely identify over 80% of the population in US. So think about how many in the same zip code have exactly date of birth, year, month, and day. So to show that you can easily find, for example, the record of the former governor of Massachusetts from the shared database. And actually, the way she did it is that she also purchased voter registration data from another data source. So then you have the precise information of, you have the name and then also date of birth, zip code, and gender. Then you can correlate this data to figure out basically the identities of the supposedly anonymized record. So in this case, we have a re-identification. So by correlating with this other data, we can point to one record and say, hey, I know this data belongs to this person. So when that happens, then this is clearly considered a privacy violation. So the second incident is this AOL, so American Online, in 2006 released a search keyword of a large number of users. So of course they anonymize the data. The way they do that is they replace user ID by random numbers. So it's actually, in a sense, it's a good thing for computer science, right? Because we want to have access to this real-world data in order to conduct our research. But at the same time, not doing this carefully result in serious consequences. So two New York Times reporters wrote articles saying that it's easy to re-identify many of the supposedly anonymized records. So in particular, this lady, they linked this search ID, this random ID to this lady. Again, if you think about what things you search for over the history, it shouldn't come as a surprise that people can identify you. So so actually for me, I guess I've searched my name DBLP quite a lot of times. So, and also you probably use your address because you want to search for things nearby. You want to search for drive direction. Your address will be part of the search history. So no wonder giving search history is really easy to identify who you are. So 3 days later, AOL pulled the data from the public. But of course, on the internet, once the data is out, you can never really get it back. So today, you can still download this data set. And in fact, we use this data set for some other research purpose, not for re-identifying, but just for using it as a realistic data set. So AOL, so again, as I point out, there's re-identification. So looking at the supposedly anonymous record, we can say, I know this record belongs to this individual. So there are serious consequences. First, the person directly in charge of the release was fired, and I think some officer was fired. And also there was a class action lawsuit against AOL. Eventually AOL settled. So AOL agreed to pay $5 million for the settlement. So as you can see from the settlement agreement, people sort of make a distinction of whether re-identification could occur or could not occur. If it could occur, you get a little bit more. So the third example is in Netflix. So I don't know how many of you know about this, but a couple of years back, Netflix released their a set of anonymized movie rating data, and they issued a $1 million challenge. So they have an algorithm for predicting how likely a user will like a movie. So what's the likely rating for a user against a movie from the user's past history and from other users' sort of ratings. So they have an algorithm, and they challenge the research community to come up with an algorithm that improve upon their algorithm by 10% accuracy, and then whoever can do that get $1 million. So in order to do this, they release this supposedly anonymized movie rating data. But then again, two researchers in UT Austin discovered that actually knowing about 6 to 8 approximate movie ratings, you don't need to know exact rating. It can be +1, -1. So this is, if the real rating is 4, maybe your guess is 3, and that's good enough. And also, you can you know roughly what time the user rated the movie, because the movie rating data published by Netflix also include date. So the date and the rating for each movie by each user. And if you know that, then you can uniquely identify individual record in the supposedly anonymized movie rating data with over 90% probability. And in particular, they showed that they obtained 50 users' movie rating history from imdb.com, and then some user will, if they enter rating on one place, they are likely also to do it in the other place. So there are likely to be similar ratings, and within the data is also similar. So they show that actually they are able to, with very high confidence, identify 2 records in Netflix and correlate that with the record they obtained from IMDb. So again, there is a class action lawsuit, and Netflix settled the lawsuit even though the financial detail was not available. And then originally they planned the second phase of the challenge, so another set of data, but they decided to cancel it. So again, here we have a case of re-identification. So finally, the fourth private incident that I want to talk about is in this kind of genome-wide association studies. So these are the studies that trying to discover a relationship between genome information and disease information. So typically, we will be studying a group of individuals, which called a study group, and also there's there's also a group of individuals that don't have the disease. So there's a study group that has the disease. There's a study group that does not have the disease. Then we want to analyze their genome information. In particular, we analyze where their genome differs. So the individual locations that genome may differ are known as these SNPs, so SNP. I wouldn't try to pronounce it, but basically SNPs. So in each of these SNP is a location in the genome such that some individual will have one variant, others will have a different variant. So the genetic code is slightly different. So so they publish aggregated information. They publish in the group that has the disease, what is the percentage of individual have a particular variant. Let's say variant A. So let's say we publish in the group that we are studying about, in the position 1, there are 43% have the A variant, and then I guess the other part has the B variant. And in the other group, let's say we have 11%, and so on and so forth. And then in 2008, a team of researchers led by Homer published the paper saying that from this aggregated information, it is sufficient for you to identify whether an individual participated in the study or not. And because this study oftentimes is about individual with certain disease, then that basically means you can tell whether the individual had the disease or not. And the real identification rely on knowing precise information of that individual. So if you want to know whether that individual is in the data set, you have to figure out that person's genome first. Maybe grab a hair of the individual and then sequence the genome to get that information, which is totally feasible nowadays. So the underlying reason is actually reasonably straightforward. So suppose we analyze this target. So then we analyze the target in whether the target has variant A in SNP1. Let's say the answer is yes. And then we also obtain the sort of the statistics, the average of SNP variant in the background population. So if the individual has, say, variant A in the first row, then we will expect that the study population, if the individual is in the study population, we would expect the study percentage is somewhat likely to be higher than the background population because this guy had this variant. So if we include this guy, then the average will be slightly higher. So it's more likely that it is higher than the background population. And similarly, if this guy, looking at the second row in the table, if this target individual does not have this particular variant, then we would expect the study statistic is slightly lower. Of course, if you look at the single SNP, this is a very noisy signal because this is just one guy. We are calculating average of hundreds of participants. So it's quite possible that even though this individual is in this group, we still get a overall lower average than the percentage, because this is sort of a random process in terms of selecting. However, the power of statistics is that even though every individual signal is very noisy, by combining many noisy signals, you can get very high confidence prediction. So if it turns out that, for example, maybe given tens of thousands of SNP positions, if over 60% of them have the study population sort of matches what you would expect, that when the target individual is in the group, that's sufficient for you to ascertain that that individual must be there. And then there's later work trying to further improve this work so that you require fewer SNP predictions to make high confidence prediction. And as a result of this study, both the US NIH, the National Institute of Health, and also the similar organization in United Kingdom changed their policy about data publishing for this kind of GWAS study. So now this kind of aggregated statistic is no longer publicly available. So you have to be a researcher, register with a website, and then only then you can get this statistic. So this privacy incident has a real-world impact. So this incident is somewhat different from the previous ones because we don't really have a re-identification. You can't really point to the thing that published and say, hey, this belongs to this individual, because we are only publishing aggregated statistics. However, what happens is we have a membership disclosure. So looking at the published data, we're able to say, I know this guy must be in there. And as we see, if that happens, the society in general consider that is a privacy violation, if this is supposed to be anonymous. So, so just to summarize, in the first three privacy incidents, we have identity disclosure, meaning that we can look at the published data and find and associate that with an individual. And you can argue this further leads to attribute disclosure, which means that by making the association, you're able to learn more about the individual. For example, in the GIC medical record case, once you learn this record belonged to, say, the former governor of Massachusetts, then you can find out when he visited doctor, for what purpose, and so on and so forth. And so also, but as we see in the case of GWAS, what happened is we have a membership disclosure. So these sort of these privacy incidents motivated the research community to design ways to publish data that do not have this problem. So in order to do that, we first have a clear definition of privacy. So when we publish data, we have to define what we mean when we say privacy is satisfied, and that's sort of the problem that motivated this work. So in the next part of the talk, I will sort of give a very brief overview of the history of studying privacy notions in the recent decade or so. So the first notion motivated by these privacy incidences is the k-Anonymity proposed by Latanya Sweeney and Parangela Samarati, motivated by the Massachusetts medical insurance company case. So they proposed the concept that privacy basically means that you are blended in a group of at least k individuals. So you are not sort of singled out. If that's satisfied, then they say it's private. So they introduce the concept of k-Anonymity, which require you to identify a number of attributes that are called quasi-identifier attributes. Basically, those are the attributes that the adversary knows or can obtain from other source. So for example, the zip code, age, or date of birth, or gender, these should be considered quasi-identifier attribute because they can be obtained from other source. The requirement of k-Anonymity is if you look at all the attributes that the adversary already know, then for any record, there must exist k-1 other record that look exactly the same. So they are indistinguishable. So this basically aimed at preventing re-identification. Now you cannot point to one record and say this record belongs to this person, because there are k minus one other records that look exactly the same based on the attributes that you know. So if you have one individual information, there are k possible candidates for matching that record. So this is intuition of k-anonymization. So it's generally achieved through either a combination of generalization and suppression. Generalization means that we replace values by values that are less specific. So, for example, in the zip code case, we can remove the last 2 digits of zip code so that more people will have the same value, so that we can satisfy k-anonymity. So this is just another example for satisfying 3 anonymity. So assuming that zip code, age, and gender are quasi-identifier attributes. So by generalizing them this way, so for every record, there are at least 2 other records that are the same. So every record falls into a group of 3. So that's the concept of k-anonymity, and this is there's a long line of work is studying various methods to satisfy k-anonymity with as little perturbation to the data as possible. But then very soon people start to realize k-anonymity is not good enough. So the concept of L diversity is motivated by the fact that if you look at this k-anonymous table, if it turns out that this sensitive attribute column that we assume the diversity rate does not know, if it turns out that they have exactly the same value in this group, then I know my individual will fall into this group. Even though I cannot uniquely identify which record is my individual record, nonetheless I can conclude my record, my individual must have, for example, if all of this is ovarian cancer, then we know it must be ovarian cancer. So then this concept of L diversity suggests that we have to require the distribution of these sensitive attributes within each equivalence class. So this group of 3 is known as the equivalence class. They must have certain diversity. For example, they must include L different values, or maybe their entropy must at least say log 2 over L. So they have to have some entropy. They can't be all the same value. So so after looking at this work, so I realized that this diversity only consider sort of apparent diversity. It didn't consider the fact that some of the distribution, for example, you may have different sensitive attribute value that they are different, but they are really mean very similar things. For example, if we have income here as a sensitive attribute value, you may have 3 value 2001, 20,001, 20,002, 20,003. There are 3 different values, but they really are very semantically close. And knowing someone have that that income enable you to learn a lot of information. So, and there are other reasons why L diversity is not sufficient. So we propose the concept of T closeness, which requires the distribution of sensitive attribute in every class is close to the distribution of a larger group. So basically you cannot learn information about a very small group, but if you are able to learn information, for example, maybe people with PhD degree tend to earn higher, that is okay, because the people with PhD degree will match a much larger group. So you are allowed to learn sort of information from larger group, but not small group. And there are actually a long line of other privacy notions that deal with various aspects of this. Sometimes people say we have a sort of alphabetical soup of privacy notions. But this fact that there are so many privacy notions also illustrate some fundamental problem, fundamental weakness of this line of approach. That is, almost all these privacy notions, they require you to identify sensitive attribute versus quasi-identifier. So you have to specify the diversity know this set of attributes, but not this. But in reality, this is not always possible. So for example, when you publish census data, you will assume one adversary may know this set of attributes about this individual, and you want to prevent this adversary from re-identifying or learn more information. Another adversary may know a different set of attributes. So unless you consider all attributes are quasi-identifier, then you can't really ensure protection against all of these possible adversaries out there. So that's one problem. And also another problem is all these privacy notions are syntactic, in the sense that they just define some syntactical property of the data you publish. So in fact, there's a very easy way of satisfying k-anonymity. That is, given the data set, I take each data set, I duplicate it k times. So then if you look at the output, every record appears k times. I'm really doing nothing to the data set, right? I'm not hiding anything, but it satisfies k-anonymity. It obviously doesn't protect privacy. And so you can do sort of a similar, and even though these examples sound very extreme, some of the algorithms proposed are actually not too far from it. So rather than duplicating every record, you can imagine you group record into group of k, and then in each group you select the sample, and then you duplicate that k times. So that's actually pretty close to some of the proposed algorithm. So this syntactic property is really not good enough, and you can come up with similar sort of algorithm that satisfy L diversity, satisfy T closeness without really providing strong privacy protection. And another way to look at the problem is all of these privacy notions sort of define what the adversary must be doing. So for example, L diversity is saying the adversary must be looking at this distribution, and then he's inferring individuals' attributes from this distribution. So that's the only thing the adversary does. If that is the case, then this privacy notion may be good enough. But in fact, adversary may know that your algorithm, when trying to do the anonymization, it's really also trying to optimize for minimum perturbation. So the fact that you produce this output may be because your input is exactly this. Because if your input include this individual, then you would produce this. If your input didn't include this individual, you would have produced a different data set that satisfies this property. So exploiting the knowledge of the algorithm, you may be able to learn precise membership information, even though the output satisfies all these properties. So this motivated, well, I guess they're, at the same time, so another line of research grew out the theoretical community, serial computer science, and also cryptography community, is this concept of differential privacy. So differential privacy tries to define privacy by defining privacy as even if your data is not in the input data set, the output should be similar. So sort of the thinking process goes like this. So if you have a choice of whether to include your data in the data publishing, and if you are worried about privacy, then you decide to withdraw your data. So if your data is not in the data set, then there's nothing you should be complaining about, right? We are publishing other people's data. Why do you complain? If as it turns out, when your data is in the data set and when your data is not in the data set, what we are outputting are very, very similar, then that means there's no reason for you to pull your data out, because anything that could be learned about you when you include your data could also be learned even when your data is not there, when you don't have a privacy concern. So then if we satisfy this, when we are publishing the data, removing any single tuple will result in essentially very similar output, then we satisfy privacy. So that's what differential privacy is about. So if we look at the formal definition, we have this concept of neighboring data sets. So given two neighboring data sets, and given this O denote the output event. So we identify output event, and then we analyze the probability this output event occur when the input is D, and the output event occur when the input is D prime, and we require the probability for this output event to be very close, so to be bounded by this equation where epsilon, if epsilon equals 0, then basically the output distribution must be exactly the same. If epsilon, typically epsilon is chosen to be a small positive number, like maybe 1 or maybe 0.1, sort of in that range. So that's the concept of differential privacy. And in fact, there are two different versions of differential privacy. Depending on how you define two data sets as being neighbors. The unbounded version of differential privacy say two data sets are neighbor if one is obtained from the other by adding one tuple or equivalently removing one tuple. So the two data sets have slightly different number of tuples. One had n, the other had n minus 1. So this sort of corresponds to the scenario I described earlier. If you are concerned about your privacy, take your data out. But then you have n minus 1 tuple, but the output is basically the same. The distribution is very similar. So why pull your data out? And bounded differential privacy define two data sets as replacing one tuple by another tuple. So then the two data sets we are comparing always have the same number of tuples. But again, the concept is similar, so that you withdraw your data instead of replacing it with maybe a random record or maybe somebody else's record, the output turns out to be very similar. So differential privacy has some nice properties. So it's composable in the sense that if I have two algorithms, they both satisfy differential privacy, and apply the algorithm to the data, and I output both of their output, then the results still satisfy differential privacy. It's just that we need to add the epsilon up. So because we slightly increase the adversary's ability to distinguish between the two cases. So in this, for this reason, this epsilon, often known as the privacy budget, you can divide epsilon up, some for this action, some for this operation. Because they need to add up to your total limit of epsilon. And if we have a counting query, then it's relatively easy to satisfy to produce fairly accurate answers while satisfying differential privacy, because changing one tuple affects the result by at most 1. And if we are asking, if the true result is much larger than 1, then adding sort of a little bit noise will satisfy differential privacy, but also preserve sufficient accuracy for the query outcome. On the other hand, some queries are very difficult to answer while satisfying differential privacy. One example is max and mean is similar, because if you consider, let's say, income, if everyone, let's say, everyone has in the group have income, let's say, less than 200,000. But if you suddenly throw in someone, I don't know who, Warren Buffett, Bill Gates, then the max will dramatically change. So then, in order to satisfy differential privacy, to tolerate change of one tuple, if you want to add noise, the amount of noise will basically totally destroy the utility of the data. And also, differential privacy is often used in one of two settings. The interactive setting is given a query, we will answer it to satisfy differential privacy by adding some noise. And then, so we have a sort of wrapper which is able to answer multiple queries. So the problem with this approach is each query answer will consume a little bit privacy budget. And once you've used all of them, you cannot answer any new query. So it's like I have this data. I can answer a couple of queries for you, but once the privacy budget is up, nobody can ask. I cannot answer anyone else's query. So that's not really realistic. So the second setting is, given the data set, we first publish a synopsis of the data, basically extract information that we think are critical for doing all kind of data analysis tasks. And then we publish this synopsis in a differentially private way. And then after we publish this, then you can do anything you want with this synopsis. Because so long as the synopsis is published to satisfy differential privacy, anything you do later will not violate differential privacy. So differential privacy, as you see, makes some query very difficult to answer. So there's a line of research trying to relax differential privacy so that we can sort of answer more queries and answer them more accurately. So there are different ways of relaxing differential privacy. So I think I'm going to jump directly to this slide. So one relaxation called epsilon delta differential privacy is now we no longer require this sort of strict probability bound. We sort of allow a small probability when this bound is violated. So we don't require D and D prime always output, the probability bound for any output event is always bounded. So we have a small probability delta, which maybe, let's say, 10 to the minus 5 or maybe 10 to the minus 7, so that we can violate this equation. And another relaxation called the differential privacy under sampling, which try to exploit the intuition that there's really no reason for someone to know exactly what other data are in the data set. So the adversary may, for example, in the GWAS incident, the adversary know one individual's DNA, one individual's genome, but there's no reason for the adversary to know everyone else also in the study. So the adversary only have statistical knowledge about other individuals in the study. So perhaps by restricting adversary to have only statistical knowledge of the background data D, and the adversary tries to distinguish D with T and D without T. So by requiring the adversary to only have statistical knowledge, we weaken the privacy notion, and perhaps we can answer certain queries more accurately. And this is captured by this notion of differential privacy under sampling, which we developed in a paper last year. And also there's a series other papers challenging differential privacy. So one piece of work argued that differential privacy is not robust to arbitrary background knowledge, which is a claim that is made in some paper in differential privacy. And here at Purdue, Professor Clifton and his student developed the notion of differential identifiability by motivating the fact that it's difficult for you to choose epsilon. So how do you decide this value of epsilon? So they introduce another notion. And also another paper, this by Cormode, saying that even if you satisfy differential privacy, you can still have attribute violation. So basically what he's saying is, even if your data is not in the data set, they can still learn information about you. For example, if somebody published information about Purdue CERIAS faculty members, even if my data is not specifically included, people can draw conclusions about me from that data set. But I actually believe that's really not a privacy concern, because it's really, you can require publishing data does not leak any information about you. I think requiring simply that you have the right to pull your data out is sort of sufficient privacy protection. But all this work of different relaxation of differential privacy and criticism of differential privacy, I believe motivate a more general privacy framework. And we introduce such a framework by exploiting the observation that what society believes to be privacy violation is membership disclosure. So in all the privacy incidences, if you're able to assert that I know this individual in the data set, then there's privacy violation. And I believe the opposite is also true. If you cannot publish data, you cannot identify anyone and say he's in the data set, I believe this is good enough for privacy. So the intuition for the membership privacy is we want to protect any entity's membership, so not just one individual. So every individual's membership information must be protected. So to make this precise, we assume that the adversary has some prior belief about what the input data set could be. The adversary is uncertain about what the input set it is. So he can have a probability distribution, assign a probability to every possible data set. So this is the adversary's prior knowledge. And from that distribution, you can calculate what's the probability that the adversary believes the tuple T is in the data set. So basically by summing up the probability of all data sets that include the tuple T. And then after the adversary observes what's outputted by the algorithm, the adversary now have seen something which is a result of applying algorithm to an input. So then the adversary can use Bayes' rule to compute after seeing this, what is the probability of each data set? So, and by updating that belief, we can calculate the new probability of T's membership. So for example, maybe if my algorithm just publish max, and then I have a data set of income, if I see the max value equals the value of, let's say, Warren Buffett's, let's say, net asset, then I know Warren Buffett is in the data set. So the posterior probability is 1. The prior, maybe whatever value I assume. So the membership privacy require for any tuple, this posterior belief should not change too much from the prior. And of course, whether this holds or not really depends on the prior distribution. For some distribution, maybe this holds. For some, this does not hold. So membership privacy is defined relative to a family of prior distributions. So this is the formal definition. So maybe this is the last thing that I will sort of explain in detail in this talk. So I guess it is maybe a little bit intimidating looking at this long definition. So let's try to sort of analyze them one by one. So the privacy notion is relative to two things. One is this D, which is a family of probability distributions. So that basically means that this is a set, and every member of the set is a probability distribution over the power set of U. And U is a set of all tuples, sort of all possible entities. So every single distribution within the family will assign a probability to each subset of U. And there's the second parameter is gamma, which sort of specifies the privacy bound. So the requirement is for any distribution D in this family and for any output event S, we have the, and for any tuple T, this is the prior for, before I know anything, the prior belief of the T is in the data set, and the posterior belief is here. So after I have observed on input T, the algorithm A outputs something that is in S. After observing this event, the posterior probability that T is in T is this left hand. So this left hand can be larger than the right hand, but cannot be too much larger. So gamma sort of bound how much this increase can be. So there's also a second equation which sort of bound how much the probability that T is not in the data set decrease. So to understand why we need these two equations, let's look at this example where we set gamma to be 1.25 and assume that in the first case, so we're examining two cases. The first case, the prior is 0.8. And then according to the first equation, the posterior should be less than 0.8 times 1.25, which actually turns out to be 1. So then if we only require the first equation, then in this situation, the diversity is able to conclude with a 100% certainty tuple T is in the data set and still satisfy the privacy notion, which is sort of not good. So the second equation says this probability is also the probability that T is not in T is also is lower bounded. So basically the probability, the posterior probability is upper bounded by 1 minus this equation, which turns out to be 1 minus 0.16. So the two inequality taken together require the posterior probability to be at most 0.84. So gamma equals 0.25 means that you can increase from 0.8 to 0.284, but not larger. And when the prior is 0.2, the first equation is a tighter one, which give a probability bound of 0.25. So you can increase your confidence in individual in the data from 0.2 from 0.25. So you learned a little bit about the individual's membership information, but it's not much. It's bounded. So that's the concept of positive membership privacy. And analogously, we introduce the concept of negative membership privacy, which says the positive only says you cannot increase your confidence in individuals in the data set, but it allows you to say, for example, when I see publishing max income, if I see the value is say 200,000, I know Warren Buffett is not in the data set, right? So this is allowed if we only require a positive membership, but this is not allowed if we also require a negative membership. So we obtained a bunch of results from membership privacy. The first one is that you can't satisfy membership privacy if you require this to hold for any distribution that is possible. So when you require this, you basically output things that has no utility at all. So this means that we have to make some assumption about the adversary. And we also showed that differential privacy, both the unbounded version and the bounded version, are really special cases of membership privacy. In particular, they require independence assumption. So for example, unbounded differential privacy equivalent to the case where all the distributions that are allowed are within which the tuples are independent. So the probability of any data set T can be written the product of the probability pt for each t in the data set and the product of 1 minus pt for each t that's not in the data set. And bounded differential privacy is equivalent to membership privacy where the distribution are mutually independent distribution restricted to all of them have a fixed length. So it turns out that the proof for this equivalence, bounded differential privacy equivalent to this family, membership privacy for this family, is the most technically challenging part of the work. And we also show that differential identifiability turns out to be another special case of membership privacy, and as it turns out, in fact, it's a sort of a special case of a bounded differential privacy. So even though it's introduced to motivate weakness in differential privacy, it turns out to be actually a special case of differential privacy. And also differential privacy sampling is also a special case. And finally, you can also define new privacy notions in this family that are not already proposed. And under this new, sometimes weaker privacy notions, you are able to do things that were impossible with differential privacy. For example, if we consider a single distribution where every entity has 1/2 probability, then we can answer a max query with very high accuracy, but while still satisfying this privacy notion. So this slide sort of summarizes the situations. So within the family, we can instantiate it in different ways. So the paper investigated these different cases. So if you consider the largest family, the set of all distributions, you basically satisfy require to sacrifice utility totally. If you limit yourself to mutually independent distribution, you get unbounded differential privacy. If you further limit that to what value the probability can take, you can obtain this differential privacy on the sampling. You can also obtain our new privacy notion. And in the other branch, we restrict distribution so that all data sets have the same size. We get bounded differential privacy, and then a further restriction get differential identifiability. So to conclude, we have introduced membership privacy framework. This is motivated by real-world incidents. And this, we believe, capture what the society views as privacy violation. And this improved understanding of existing notions, and we believe it also provides a principled way to define new privacy notions. And there are a number of interesting future research directions. So one is to investigate other instantiations. For example, mutually independent distribution where the probability of every tuple is bounded, both upper bounded and lower bounded. And also, sometimes you don't really have a well-defined sort of a universe of entities, how to apply that. And finally, I think there's how to do this inference with uncertainty is really goes beyond simply applying Bayes' rule. Because sometimes the adversary didn't really have a good prior knowledge. So how do you really capture that situation? Okay, so almost out of time. Any questions? Yeah, so this conditions of composability means that differential privacy, as I said, has this nice property of composability. But it turns out that several other privacy notions, like differential privacy under sampling, doesn't have that property. So it's a very interesting question for what kind of family this membership privacy is composable and for what kind of family it is not. So this is, from a theoretical point of view, it's very interesting. Okay, so if there's no more questions. Okay, so I guess that's it.